I didn't mind.
Hello.
Hello, Giuseppe.
How's it going?
Hey, let's go.
Alright.
How do I go back and share?
Yes. Because I really want to play more squash.
Precious season thing.
I used to play dancing. I was supposed to go this morning, but I just couldn't find a dance in the racket. So I used to buy one.
Just play with your hands.
No.
What a sports round.
Magic.
I think we really had to get the ball in with a shuttlecock in. Give that a go though.
Right, so we're gonna wait 1 more minute maybe, so other people can join, and then we can start. How many people were attending the lectures online last week? Do you remember?
I think it was 3-ish.
Okay. You're expecting 17 people in total.
Yeah, there'll be some people in the rooms I think as well, maybe.
David was here last week.
Yeah, I was.
Rory was also here. I don't know if he's.
I've not seen him this morning, and Alex isn't there from Edinburgh.
Okay.
Edinburgh room looks empty.
Just a quick check, can people hear me okay online?
Yep, seems good.
Thank you.
There's Alex.
Oh,
You can also see the slides, I guess.
yeah.
Great, thanks. Classic start of a meeting, right? Can you hear me okay and if you see the slides? Right, why don't we slowly get started? So welcome to the first part of the QCD module. I'm Giuseppe. For people who don't know me, I'm a postdoc at Glasgow working on the advocate experiment. And I'm also the course organizer. So any questions on the course, just send me an email or come and find me in my office. So last week you had a brief introduction of what the expectations for the course are. So today we start with the first module, which is QCD. Then next week is again QCD, second part. So today is going to be more on the theory and how experiments help developing the theory. Next week is going to be more experimental, so we're gonna have some highlights from previous experiments or current experiments on QCD measures. And then, then you have Monte Carlo, Electro Week, and Beyond Stellar Model in this order, I think, if I remember correctly. Any questions on the course so far? Any doubts or anything you want me to cover? No? Okay, let's jump in.
Sorry, could I ask a quick question?
Sure.
I just joined there, so I was just wondering, did you cover what was happening in terms of the literature review? Is there any information about that yet?
No, I didn't say anything in this meeting. I was since then next week is going to be me again. I'm going to do the announcement next week. That's okay. So
okay, that's fine. I just wondered if anything had been released yet, but that's cool. Thank you.
No problem. Thanks for asking. But I think Mark gave general idea last week. So it's going to be a list of paper available on the course website. It's a first come first served approach. So send you the list, and you drop me an email saying I'd like to cover, or maybe you can provide your top 3. And then if one of those is available, I can assign that to you. And then this year is slightly different compared to the rest. To the previous approaches where we had a set of problems and a literature review. So this year it's literature review only, but we're going to ask you to review one of your fellow student work. So it's going to be a peer review. In the end, we're going to mark your review and what the other person thought about your work. That makes sense. Okay, but I'm going to explain everything in detail next week.
Okay, cool. Thanks.
Thanks. Okay, what to expect from the QCD module? We're gonna give you some tips about what to find, where to find the information I'm gonna describe today. I'm gonna talk about the scattering experiments that led to the development of the QCD theory. And then what is QCD, what kind of properties and observable we can use to probe it. And then I'm going to show you some recent measurements like from the LHC or from HERA or from the Tevatron. And so just a summary at the end of it. So as I said, it's a survey of experimental measures of QCD at high and low energies. I'm not an expert on everything, and it's going to be very hard for me to cover all the QCD part in 4 hours. So it's including the measurements at experiments. So I'm going to give you the main highlights. Of course, there are other good books. It's just a selection, and you're encouraged to have a look at those in case something is unclear, or we can also discuss it offline. But please, I don't think I have the chance to monitor the chat on Zoom. So if you have any questions, please just jump in. Okay. Well, I guess at this level, we all know what the strong interaction is. It's one of the 4 fundamental forces, and is the one that is responsible for cohesion of the nuclei. Must be strong because if nucleons like protons or neutrons are present there, and it's very hard to study its substructure. So that has to be very strong and stronger than the electromagnetic force, and has only to be effective at short distances. Right, so we know how big the radius of a proton is, so it has to be less than that. It's very easy for us to say now, that there are 3 generations of quarks, which are the one in purple here, top left, and then the force is mediated by gluons, which are the top red box. In the 4th row, but obviously it wasn't so trivial in the past. So I think when the proton has been discovered, which was 1917 or something around that, people started to ask some questions. Are they elementary, or is there something else underneath? So in 1964. Have 2 independently two independent approaches from Gell-Mann and Zweig, who actually proposed the names quarks and aces. I think the name quarks comes from a James Joyce novel, if I remember correctly. So they proposed that the nucleons in general are composite particle built from three basic blocks. So as I said, they already discovered the proton. So the way it was discovered was by Rutherford using scattering experiments. So why don't use the same approach to do some studies on the proton substructure to unveil the force and the charge distribution that is involved. Scattering experiments are relatively easy. Just need to follow one simple rule that I'm quoting here. So it's basically that it's about the wavelength of the probe particle that scatters off that target. So that means that in the end we need high energies to achieve the large momentum transfer in the scattering experiments, hence probe the target particle. So let me start with the elastic electron-proton scattering, or EP. It's been observed at SLAC, so in California, using a 22 GeV linear electron accelerator, which is very different from the kind of center of energies that are involved in current colliders. So people interpret that in terms of QED, so the electromagnetic force, or the theory that describes the electromagnetism, as the exchange of a single photon between the electron and the proton. And this measurements show that the process, the cross section at large angles was much smaller than the one when you're using electron positron scattering. So at the time, it seemed like something that was not elementary. So that people started thinking there was something else. There's something we're not considering here, though. Can we really regret the recoil? The answer is no, because then we're talking about energies from 100 MeV to several GeV, and this is the radius of a proton, and this is its mass. So we cannot really neglect that. So people also, so it's not really an elastic scattering, right? If you consider the recoil effect. So people start plotting these distributions on the left hand side. So you have the E prime on the x-axis, which is the accepted scattering energy, emitting a spectrometer, which has been put at 10 degrees. Angle theta. I know it's very small here, but perhaps you can read it, this label here. And we're using 4.9 GeV electrons to scatter off on the proton. And on the y-axis, you have the differential cross section. So you can see this sharp peak here, which has been scaled by factor of 15. So it's just for simplicity. There's nothing complicated here. So it's just because the peak is so wide, it's so sharp, and it has so many entries there. It has to be scaled to be in this plot. But this sharp peak is what you expect from elastic scattering. But then there's something else here. There's this peaks on the left hand side, which are highlighted by the black and the and the red bar, which are which represent the excited proton states, so the particles like delta plus or delta plus plus, and then for the red part is that's where the proton starts to break up. So is that you can actually see there's something moving inside the proton. So you can actually see its components. So the existence of these resonances, so the one highlighted by the red and black bars, demonstrate that the proton is actually not elementary. There's something else. On the right hand side, you have a very similar sketch. So you can see when you do the scattering experiments, and you're using an energy which is much lower than the one is actually needed to say the substructure of a proton. Then when you start increasing the energy, you can actually see these other peaks other than the one at 1. And then when it's much higher, you can actually see there's a peak at 1/3. And now we know that protons are by 3 quarks. So that's why you have a peak at 1/3. I'm gonna go back to this plot later. So I promise you that I'm not gonna do the math, but this is the only part where you can actually do some calculations in this lecture. So let's think about it. So K in this case, looking at the Feynman diagram on the right hand side, is the moment of the electron, and K prime is the one that is the transit moment of the electron after the scattering. So then you can interpret this as a formal momentum transfer by lowercase q squared, which is defined by k minus k prime squared. Or if you want to work with positive quantities, you can define capital Q squared equal to this one. So now as a trick, this has to be interpreted as a Lorentz invariant. So we need to define this new variables, which are called x and y, which are a function of the momenta involved from the electron and proton side, and then you can plug in these two new variables into the Rosenbluth cross-section formula. So you can actually have this new formula. Okay, sometimes it's here, sometimes not. I don't understand. Where you can actually see there are these F1 and F2 functions, which are the proton structure functions that depend on x and q squared. But from the interpretation of Bjorken, these two functions only depend on x at high values of the for momentum transfer, which is the property of scaling. So scaling means that it only depends on, so that the structure functions only depend on x, so that there's this quantity here at high values of the transfer momenta, which means that the photon scatters off charge point like constituents of the proton. So that's why the idea of having quarks is very instrumental at this point, and also it started to be proven from both experimental and theoretical side. This is called the Bjorken scaling. So in this case, x is called the Bjorken scaling variable, and is a way to measure the inelasticity of the process. So that means so I'm going back to the expression of x. So if x is 1, that means that the process is elastic. But if it is between 0 and 1, you can actually see that I have an inelastic process. So going back to the picture I was showing earlier, you can actually see now that the peak that we observe at x equal to 1/3 is not straightforward to interpret. So we are assuming that the electron scatters off on a nucleus constituents, and the Bjork scaling x can be interpreted as the formula I was showing before, but they're also divided by the number of constituents. In this case, we have 3 number of constituents, so hence the peak at 1/3. Okay, but then people were confused. Right, we found that there are these point-like constituents on the Bjorkian scaling, but they didn't have a model at the time. So Feynman proposed the Korf-Barton model to account the scaling of proton constituents, which are now called partons. Remember that at the time they didn't know about the gluons property, which I'm going to describe in a minute. Because it's mostly these constituents that now we know that are quarks. So in this model, the deep inelastic scattering, so high Q squared, is defined as a single photon exchange between the electron and the parton involved. And in this sense, the structure functions F1 and F2 are the result of a magnetic interaction. So F1 is a magnetic interaction, vanishes on scattering of spin 0 particle, and F2 measures the momentum distribution of the charged particle within the proton in terms of x. So it's purely about proton properties. So most of the concepts that we have now in QCD are inherited by QED. It was already on a very well-established theory at the time. So the structure function can be defined in this way, where EQ is the electric charge of the constituent, and then we already know what X is, and then Q is the probability of finding a parton that has a momentum fraction between in the range of X and X plus dx. So in this sense, F2 is the sum of momentum distribution weighted by X and the electric charge. Moreover, at the time, people were thinking that the structure functions are not independent, but can actually see a correlation. That's why they proposed to use this R, which is basically the difference of F2 minus F1 when the times 2 times X, which was measured as approximately to be nearly 0, which is called, this is called the Callan-Gross relation. And this is what we would expect to have if these basic constituents have spin half. And then there was also a case where when people started to separate to the two groups of balance constituents, which are those that actually determine the quantum numbers of the nucleon, and then the C constituents, which are only visible in deep inelastic scattering due to the electric charge. But the C are basically a pair of constituents and anti-constituents that annihilate each other every time. They cannot actually, they don't actually contribute to determine the quantum numbers of the nucleon. They are present, but they don't contribute to that. Which is something we're established that even today we know that we have valence quarks and C quarks. The Callan-Gross relation seems a bit naive from my introduction, but I actually has been measured with good accuracy. So the if you take again the Rosenblatt cross-section formula in the spin half case, and then you do the calculation and you do the experiment that they did at the Slack, here is a plot about this. You can actually have a plot to xf1 over f2 on the y-axis, and then you have x on the x-axis. You can see that actually the points are consistent with the unity within the experimental bar. Of course, they didn't have the precision that we have today to do this kind of experiments, but it's quite consistent. So it seems like the naive quantum model works in some cases. It makes sense, and it actually will serve as a basis for the proper theory. So to summarize what we discussed so far, what we achieved, quantum-particle model is a good method to deal with strong interaction and focuses mostly on the effect of particle distribution. If you interpret as an electron-hadron process, now it becomes calculable in terms of first-order QCD process. So we are inheriting most of the approaches that were in QED. But then leaves some open questions. What are the Spartans? How they interact with each other within a proton? Can we observe them outside the nucleon we are considering? And what prevents them to just go out and like make nucleons fall apart? But based on experimental observation, partons must be almost free to account for scaling. But also there should be a very strong intercore force that prevents them to.
So sorry, just a question.
Please.
At this point, there was no understanding of, oh, they are gluons. I was
That's
just
right.
thinking of, oh, there are valence quarks and then a sea of quark, but no real explanation of what causes the sea of quarks.
Exactly.
Okay.
Exactly. So the concept of glue, as I said, so most of the concepts are inherited from QED. So if the time people were thinking that gluons, so the mediators were sort of a photon that does not carry the electric charge, but mediates the force. But we're going to see in a few slides that this is not the case, of course. But yeah, there was no idea about the gluons, but just generally the various type of quarks.
Okay, thank you.
Worries. Yeah. So about the concept I was saying that most of the approaches come from QED. There are the sum rules. So we can already start talking about particle distribution functions that describe the structure of a hadron and take into account. Sorry, it's something that we know today. So gluons, valence, and C quarks. But now, so you can actually. So this is an approach a posteriori. So we know now that present protons are made of two up quarks and one down. So if you want to define what is what are the particle distribution functions for a proton, you need to do a combination of the up and down particle distribution functions. This is where this ux and dx represent here. but at the time, if you want to do the sum rules that are present already in the QED theory, what you expect is actually to have if you do these calculations here, to find 2 and 1, so only account for the valence quarks into that. This is what you expect, but actually what's measured, if you do the calculation, like the sum, or when you consider the quarks and anti-quarks, where you would expect to have 1, you can actually get half. So, which means that the 3-quark model of protons is overshooting the measured size of the structure function by approximately a factor of 2, which means that 50% of the proton momentum is not carried by quarks. So this is where gluons start to play an important role. So about the strong interaction, so the quark-particle model show that quarks are real, but now we need to find a proper theory. Main problem, gluons. Are they like photons? So we're saying that they don't carry the electric charge, but can mediate interaction between quarks. We know for sure that quarks are fermions for their spin half. So the total wave function must be antisymmetric under the quark interchange. So the wave functions, of course, are represented by 3 components. I have a formula here, which is symmetrical overall under exchange of quarks, which is something that is not allowed in theory, because we will break the Pauli principle. That has to be asymmetric. So this is already assuming the fact that the SU3 group is the one that describes the theory. So the solution to do that is introduce a new quantum number, which is color. So people try to use different groups, and actually SU3 is the one that describes the actual strong force theory. And so that's why from the name color, you get to the quantum chromodynamics, hence QCD. If this sounds a bit naive again, there's the delta plus plus situation, which is a resonance consists of 3 up quarks. So it is an excited state of a proton. You have actually 3 up quarks. So it's been measured that the spin of this resonance is 3½ and has positive parity. So from these, we assume that this angular momentum is equal to 0. So that means that it has a symmetric spatial wave function. So to get to this value of spin, that means that the spins of the 3 quarks have to be parallel, which is again a problem under the Pauli principle, which is a terrible thing, because it's a cornerstone of physics and chemistry. There must be something else that can save it. And indeed, if you consider color, which can some very 3 convenient values, RGB, if you introduce the fact that gluons are also carrying this color charge, let's call it this way, plug it back to the SU3 group theory, that means that they can also experience self-interaction. That means that a gluon can split, for example, into pair of pores. The photon does that too, right? But also the gluon can interact with another gluon, which makes things extremely messy, but also makes sense in the theory concept. So you can have vertices with 3 gluons or 4 gluons, and this leads to the Gell-Mann matrices, which represented the structure of this SU3 group. And there are 8 of these matrices, which means 8 gluons, 8 kind of gluons, if you consider the color combination. So why SU3? Again, if you consider all possible correlation that the color or the color the gluon might carry, so in the end you have 9 combination, but you can actually do a linear combination of the neutral one. So red and anti-red, green, anti-green, blah, blah, blah. So you can actually lead to 1. Plus there are 8 others which are written here. So that means in the theoretical language that the outcome is become a combining of a 3x3 representation of the SU3 group. That's what there's 8. So there's an octet and a singlet. The singlet has not been observed in nature, so it's only the octet. That's why the 8 gluons have been found experimentally. So that's why the SU3 group works well. Because if you were considering the symmetric color singlet, the gluon will be colorless and unconfined. Well, actually, we know experimentally that that's not the case. You can actually see that. So,
I just have a question.
please.
I don't think I fully know what justifies the fact that gluons do have color charge. Like what makes QCD different that QED doesn't have, let's say, a photon with charge? Is it to do with the SU3 symmetry or?
Yes, SU3 symmetry is known abelian. We know that. So that is one effect. And also, of course, this is very convenient, the fact that we are now introducing this new quantum number to account for well the what's it called? The wave function. Sorry, that was miscue in my mind. So it's based on the observation, for example, in a delta plus case, but also is a manifestation of the SU3 symmetry and is known abelian nature. So that which is different with respect to SU2 and so it's U1 in the case of the of QED. So it's a purely manifestation of that symmetry.
Okay. Thank you.
Thanks. So where was it? It's actually okay. Any questions at this point? No, because we're roughly halfway through this, so I was gonna propose a break now, like a 5 minutes break. Gonna meet again 10:45.
You can force the room between. You can't force the room between. It's too fucking good for us again. You coming tomorrow?
Hmm?
You come to watch rugby tomorrow?
Yeah, I mean, actually saying to Elliot, so I'll be at Innocent Garden on Saturday to watch Wales Scotland.
Okay. Yeah, because we're looking for somewhere to book or
Because
something.
but I think my booking is full at the moment.
Oh.
I can try to expand it. I don't know.
I don't think it doesn't go on, yeah. We're looking at Record Factory, but
Before we watched the game last year.
oh, so they do show review.
It depends. Is there a football match in? Last year was Old Firm in one room.
There's no Old Firm. Oh.
Right, and then the other room was this.
No, there's no. I don't think there's any big matches. Big football matches. I thought someone had booked Dram. I booked Dram for tomorrow night, but for Saturday. Oh,
I try to try kitties.
Oh.
I've watched it. Because you have a booth inside of
The
it.
one on Derwentford Road. Yeah.
Yes.
Oh,
Because no one does.
Me going to
Alright.
Katie's is like dragging you to a fucking waffles cafe or something. I don't know. It just feels wrong.
Okay.
It's like just really bad trash. It's just, well,
I was hired.
I think it's hard.
It's not right to know.
I don't plan.
Do you use top CP toolkit much?
Yeah.
No.
Never used it. I did a bit of analysis stuff for the flavor type part. No, so. But I can have a look.
Maybe at some point. Maybe once my qualification test be flavor tagging and
Yeah, I don't know. I've all this stuff.
yeah, I think Russia is completely.
I'll switch with. Oh, he was saying okay.
oh, right, let's go.
Got confused with what it was.
I don't know either.
When did they first start to improve sort of the sea, like the sea of all the other quarks inside of the proton?
Yeah.
I think when they continued doing this discovery experiment, at some point they reached the energy capacity. They actually broke the seed course. I can't remember when exactly. Because then
Basically, did this idea sort of come along at the same time?
yeah. Because then when you do the math with the sun moves, you see that of course of course you need to consider both the balance and the sequence, otherwise it's going to be, if you just consider the balance portion, it's going to be less than half as we and then the fact that the gluons means what important force pairs or so complicates the picture. Yeah, the
Yeah.
concept of fluency comes later, but of course the sum rules have to go. It's very convenient that yesterday there was what's called the CERN colloquium or something like that. They said it's the birthday of the QCD as well. Well, it was last year, but then there are sort of two.
Do any of you follow F1? Oh, never mind.
What time is it on?
Tomorrow?
Yeah.
I think the match is at 8. I want to vote for 7.
Is it okay if I join or is that?
Yeah, of course. Yeah, no, I booked it for 12.
Yeah.
So
All right.
but only if you pass me.
Well, gonna see that. Yeah. Okay, shall we start with the second part? Any other questions? Maybe if the break helped? Questions or curiosities in general?
I just have a question. So, I know they use deep inelastic scattering in order to determine how many constituent particles, because they saw a third. But how did they know that there was a sea of quarks within the proton? How could you determine that experimentally? That's what I'm wondering.
And then how could you tell the difference between those quarks and valence quarks?
Yeah, so for example, let's take a simple case, which is the proton. So now we know is that the valence quarks are 2 ups and 1 down. So as they increase the energy with the scattering experiments, they actually saw that other kind of quarks can be produced into that, and that the fact that basically these are annihilation between quarks and anti-quarks. So it's just a matter of increasing the energy you have at this experiment. You can actually see through the plots I was showing earlier with the resonances, they can actually find something else.
Okay.
Any other questions? No? Okay, so let's talk about properties. So we discussed it at the beginning. So the theory of quantum chromodynamics has 2 very important properties about the quark and gluon interaction, which are asymptotic freedom and confinement. So the question here is again, can we find a quark in a free state, right, outside a nucleon or a meson, whatever that is made of quarks? The answer is it's almost impossible to do that because the potential energy that is required to separate a quark from its gluon linearly increases with their distance. So when the quarks are close together, the force is relatively mild. But if you start pulling it apart, you can actually see that this increases, and at some point it reaches the threshold where if you actually snap here, like the middle part of the picture, you can actually reach the energy to produce a new quark anti-quark pair. So it's almost impossible to find them separately. So in terms of experimental evidences, that quarks and gluons are seen in colorless hadrons, and as I said, is that the energy that is required to separate them is the same that I actually need to create a new anti-quark pair. So it's very hard to find this. Then that was the confinement, asymptotic freedom. So we know that a quark can emit a gluon. We can split in a quark anti-quark pair and so on. It's going to be very messy. So that means that the initial quark is then surrounded by, well, if you think about if we reconstructed the history of a quark, that means one is surrounded by other quark anti-quark pairs, which actually are diffusing the effective color of the initial quark. So a sort of screening of this color charge around. So for simplicity, let's take a red charge, which is surrounded by a cloud of colored dipoles anti-screening this color charge. So if you want to study the red charge, you need to measure the force experienced by a probe. That can be anything. So then when you move the test charge towards the quark you want to study, you actually see again there's the decrease in the measured charge. So you have a graph here. So you have on the y-axis is the color charge, and the x-axis is the distance from the bare quark that you actually want to study. So if you are decreasing the distance, which is the left-hand side of the graph, you can actually see the color charge that the probe is experiencing is very low. But if you reach the edge, let's say, of a proton, it's around 1 Fermi, and actually see is asymptotic behavior. Basically, it's going to experience an infinite color charge. So that means there's a confinement barrier. So this anti-screening results in asymptotic freedom. So when they're close together, quarks interact through color fields, reduce strength, but they in that case they behave as free, non-interactive particles. But if you try to study one of them when it's confined, is very hard, and this is the result of the asymptotic freedom. These are the cornerstones of QCD, and I think so. Yeah, I was saying during the break, it's actually the birthday of QCD. So I think it's the 50th anniversary, right? I think it was last year, but now they're advertising. So it's actually 50 years since the asymptotic freedom has been observed, well, theorized, and then so because then in the early 2000s, people were awarded with the Nobel Prize for the discovery of asymptotic freedom. So it has been theorized and then was proven at experiments later. So in terms of observables, according to the QCD predictions, we need to observe experimentally 3 coronal states per quark. That means if you do cross-section measurements, you should see the 3 core degrees of freedom for each quark in a final state. How do quarks and gluon manifest experimentally? There's a concept of hadronic jets now, which are basically sprays of hadrons that you can actually reconstruct with your detector, which results in let's put it this way, when a quark or a gluon cools down at some point, it starts clustering with other. So going back to the confinement part, we have sprays of hadrons that you can actually reconstruct. We said that the gluons are color carriers, so that means that these jets can also be started by gluons. So we need to find them, and also we know from the theory that the gluons can self-couple. So that means that experimentally you should actually find a free gluon vertex. And then if you remember the scaling, we did some assumptions. So the scaling is of in the example earlier, an electron that scatters off a point-like constituent within a proton, which is fine. It's very helpful. But in QCD now, so it's not the quantum particle model anymore. So that is, well, that has to be broken because of gluons, basically. Is gluons again. So before the structure functions, we're not depending on Q square. Now they should. And now and then we know from QED again, the coupling constant alpha is running with the energy involved in experiments. So we expect alpha S, so the coupling constant for the strong interaction, should decrease when Q squared increases. So let's start with the coupling. So I was saying QED, we know that alpha is a measure of the strength of the electromagnetic interaction and gives the probability of emitting a photon. And this is expression of alpha. And then a factor, the square root of alpha, is associated to each absorption or emission of a photon by charge E. So you have a finite diagram on the bottom left of this slide. You can actually see the square root of alpha associated to each vertex involved here. In QCD, alpha S is very similar, where G now is the core charge. And then again, the square root of alpha S is associated to each vertex. Here in the Feynman diagram, when it gives the probability of emitting a gluon. Running constants, well, in QED, the chart seem it depends on distance from the particle due to screening again. So alpha depends on the scale, which it means the energy of the process, and is said to run. In QCD, the boundary strength also depends on the scale, so Q squared. So also alpha S is running, but it's slightly different from alpha in QED because of confinement and asymptotic freedom. But there is one regime where you can actually consider at short distances. That's where you can settle a perturbation theory where you can actually study the properties of the quark. I think it's clearer in the next one. When we think about a grand unification. So if you look at the plot at the bottom right, you have Q squared, the transfer momenta, different transfer momenta on the x-axis, and the y-axis, the coupling constant. So you can see that alpha S, which is the top line, is really high, especially at low values of Q squared. So that's when the quark is confined in a hadron. While for example, for the alpha for QED, chances that they behave very different, but almost converging at high values of Q squared. So if you study the regime when Q squared is high, you can actually see quarks as almost free particles. That's what we do at colliders, right? When for example at LHC, when we collide protons, well, bunches of protons, the value of Q squared is extremely high. You can actually consider the interaction of the proton collision as a quark that interacts with another quark from two different protons. So in terms of ground unification, we imagine that very high values of Q square at some point, the coupling constants will merge together as under one force. But yeah, here are some highlights from the ground unification theory, which I'm not gonna cover. Yeah. Color states. So we said that there are, at least from the theory, 3 kinds of colors: red, blue, and green. How can we measure that experimentally? We know from calculation, very accurate calculation of this cross section, when you have an electron and positron in initial state, and then in the final state you have a muon anti-muon pair. We know that the cross section for this process is equal to this part here. So if we were considering the same initial state, so electron positron, we have a quark anti-quark pair in the final state. In the end, the calculation of this cross section is very similar to the one from the previous process, apart from this new factor, which is NC, and the sum of flavors of this ZF. So NC in this case is the number of color, and ZF is their electric charge. So this assumes that quarks have an electric charge. So if you want to measure experimentally this factor R, you can actually do it. This is what they did as LAC and other various experiments. So in this graph, you have the central mass energy, square root of S, on the x-axis. You have the value of R on the y-axis. You can see that apart from particle resonances, you have the Z boson on the far right. There are there's the Gibbs side. That's where the charm quark has been discovered. Apart from that, the value of R is flat, which means and it's flat around some specific values. So, for example, if we were considering just this part here, this flat behavior, that's where only 3 kinds of quarks were discovered. So if you consider the central mass energy S here, can actually, if you do the calculation, it actually around 2, R equals to 2. That's where we are here. They have a couple of resonances, but then when you start increasing the central mass energy, you can actually reach the part when you can include the charm quark in the picture, and R is equal to 10^3. So that's where it corresponds here. Well, I was attending this colloquium at CERN yesterday, and people started worrying when they reached this part, but the Gibbs psi resonance has not been discovered. So people were thinking we broke QCD, so we cannot actually prove there are 3 kinds of color states. But then when they had new experiments with increased central mass energy, they found, yes, the resonances, but also this flat behavior again. So that's what it's 10^3, and then if you include the top and bottom quark in the picture, it's actually 5. You can actually see the values here. So in this picture, you can actually see that the number of color state has to be 3 kinds of color. And of course, this is a great experimental match. The existence of jets. Once again, the concept that the quartz and gluons cannot be observed directly, or if you want to call it in their bare stages. So when it's the time to think about what kind of colliders, if you want to do precision measurements, having an electron-positron collider is probably the best approach you can actually do. Because then, if you were using hadrons instead, that means there's a huge hadron activity that is not necessarily easy to separate from the part that you actually want to measure. So at the time, is the era of discovery having a electron-positron collider helped a lot. So we saw in the previous part, you can actually produce a quark-antiquark pair in the final state. But then when they cool down, they produce these jets or sprays of hadrons. So starting from this red pair of quark-antiquark. Evidence of jets. So first of all, how do you detect jets? It's actually a mixture of the detector components. Obviously you need a tracking part that for charged tracks, but then you can actually match to clusters in your calorimeter system. And this is what we're seeing here in this picture. So you have the light blue tracks in your tracking detector, and then this yellow and purple squares are the energy deposit into your calorimeter system. So the first observation of back-to-back dye jets in E+ E- events has been done at Spear, 1975. So, well, why back-to-back? Because from leading order calculations, you can if there were just two jets in the events, you can actually find them so balance and transfer momentum like this. So the angle then should be around pi. And obviously this was a big hit because it actually confirmed that you can detect jets, and also if you can detect them, that means you can measure something, and then from there opens the room for other QCD measurements. So this is the previous slide was the picture in 1975. You can actually see a small amount of energy in that kind of detector, but now you reach the point where you have an abundance of these jets. Sometimes there are too many, so you want to do some other measurements. Yeah, you have to find a way to remove them from the picture, or at least control their background. But now, so with the LAC, for run 3, there is the central mass energy of 13.6 TeV. This is a picture from a jet differential measurement from Atlas in run 2. So it was slightly lower central mass energy, 13 TeV. Can actually measure the momenta. You can actually measure the cross sections of digest events with very accurate precision. This is this dots here are compared to the next to leading or next to next leading order predictions, which are represented by the yellow part. As you see, extremely good agreement between the two. That means we reached the point we can actually do super precise measurements of QCD with exceptional precision. So now that when I say here, we're not in the differential measurement area, because we reached the point, and obviously from the theoretical point of view, we reached that level of the precision, and actually compare to this data at every level. Well, at a level at least next to leading order or next leading order, so it can actually test that QCD is a very solid theory from both the experimental and theory side, and so we can actually measure its property in different ways. I promise you the fact that there's a triple gluon vertex as a result of the non-abelian behavior of SU3, which introduces the self-coupling of gluons. So that means if gluons can self-interact, should be a 3-gluon vertex or 4-gluon vertex, like in the picture in the bottom right. So the non-abelian diagrams are the one at the bottom right. The abelian are the ones above. So if there is a triple gluon vertex, means that we have even with 4 jet events, which has been observed for the first time at LEP, where people design some very useful variables to study this non-abelian nature of QCD, like the Bengtson-Zewers angle, or the Nachman-Reiter angle, which are represented here. So the Bengtson-Zewers is the angle between the. So if you have 4 jets in the final state, you can actually build the planes defined by the 2 lowest and the 2 highest energy jets, and you can actually measure the angle between these 2 planes. While the Nachman-Reiter is the angle between the momentum vector, the difference on the jets 1, 2, and 3 and 4. So the bottom right plot in this case, you have the Bengtson-Zewers angle on the x-axis, and then on the y-axis, it says event fraction, so it's we're counting the events on their data set, and this is what happens. And here, the black dots, the full dots, are the data. And these lines here, so the darker line is the one that is for non-abelian behavior. Compare also to the gray lines, which will represent the abelian behavior. So you can generate your simulation, saying, okay, with the black line, I'm going to test if the QCD is really non-abelian. With the gray, you say, no, I want to prove that QCD is wrong, and then I'm going to do it with abelian. You can actually see that the full dots agree well with the non-abelian simulation. So that is confirmed experimentally. It's obviously great relief that QCD still works. Scaling violation. As I said, the quarter model predicts exact scaling. That means the Calandra oscillation, and then the structure function do not depend on Q square. But the quarter model ignores the fact that that there's gluon emission from a quark, or can actually experience the different inelastic scattering between gluons. So this part gives dependence to the structure function by a factor proportional to the logarithm of q squared. So the logarithmic scale violation is a property of the gauge theory, is a point-like fermion vector boson couplings. And here's the evidence. So that's what they did at Zeus at Hera, where they again, you have on the x-axis you have q squared, and then on the y-axis you have f2, the structure function. You can actually see that perhaps at low energies or low values of f2, actually see this kind of flat, but then as you increase q squared, you can also find at high values of f2, it actually starts to have a trend. So f2 increases with q squared as a small x, and decreases at a large x. So it's in this picture you can actually find a comparison between the data at Zeus, which are the red dots, and then the line is the prediction at next leading order. So scaling violation is also confirmed. Only one property left, which is the running of alpha s. So in quantum field theory, the coupling constant describing the interaction between two particles is an effective constant, which depends on the value of q squared. We saw how alpha s behaves as a function of q squared earlier. Like low values is extremely high, so it's impossible to actually study the constituents of a proton, for example, because they are confined, and asymptotic freedom also makes them experience a very strong barrier at 1 Fermi. So, but if you move very close to the quark, you can actually see them, and then alpha s reduces. But the trick here is that if you do your experiments at very high values of q squared, you can actually see the partons, the quarks in a bare state. So that's where the term perturbed QCD comes from. So if you were to do the calculation, first order perturbation calculation in QED yields to this formula for alpha s as a function of q squared. You can actually see a few parameters there, including lambda, which is the only free parameter of QCD. In this picture, NF is the number of cores involved. That can be resolved only at very high q squared, so that's the kind of resolution you can actually use to study the quarks. So lambda is the only free parameter, and it was found it's a sort of threshold. So if you pass lambda, you can actually move into a perturbative behavior of the theory. They can actually study the constituents as they were free. But if you don't pass that, you are at high values of alpha s, so it's almost impossible for you to do that. And but lambda is set to 150 MeV, by experimental observation. So if in this case, so if your Q squared is much higher than the lambda square, then you are perturbative. So as we are the LHC, for example, now. So if you pass that threshold, that means that you can actually do some approximation and find define something for the perturbative regime, which means that you can actually use this very powerful tool, which is the factorization theorem, which states that the cross-section of any QCD process can be written as a convolution of the Parton distribution functions, PDFs, which here are represented by this Q1. So Q1 is work 1 or Parton 1, whatever, inside the P1, so the initial hadron you want to consider, and FQ2 is for the other one. So the cross-section of any QCD process can be written as a convolution of these PDFs with a partonic cross-section, which is this sigma hat here. That means, for example, if we're colliding protons and you consider an interaction between quarks or gluons from different protons, and you have something else in the final state. That is the cross section that is sigma hat here. So it's very powerful because that means if you know sigma hat, you can do the calculation, and then PDFs. A bit abstract now. I'm going to explain this better next week. Are universal. So if you're colliding protons, that means that PDFs can be recycled for each calculation. So in the end, you can actually measure the final sigma P1 and P2 very easily. This is a very nice advantage because while PDFs are non-perturbative objects, if you do a calculation once, you can actually recycle them and use it for other calculation. Evidence of running alpha S is a very nice plot by Atlas, again, where you have alpha S function of Q here, and you actually see how different experiments confirm the running of alpha S. So you have experiments from the past, so D0, which was at Tevatron, at Fermilab. And then you can also have modern experiments like Atlas and CMS. You can actually see that they span the values of Q from a few, but from 10 GeV maybe to more than a TeV. So it's something very well measured, very well is established. Is a further confirmation of QCD. So it's the end of today. So let me quickly summarize what we discussed this morning. So I really hope that I made my point that QCD is a very well established theory, but it's a strong interaction. It took a long time actually to prove it. We started from the discovery of the proton in 1917, So and then people started asking, is this an elementary object or not? But they started doing an experiment. They found that actually there's something else. We started doing experiments with the 22 GeV collider. And they already found some resonances. That point you can do some assumptions. You assume scaling. That means point-like particles that are building the proton, and then these particles are fermions. So we move it to scaling, Calandra selection, etc. Then people started formulating the quark particle model, which actually works. Some rules from QED are working, but that means also the people were neglecting the fact that gluons are playing an important role. Then on the way to formulate QCD, they started investigating the groups that can actually describe that theory. SU3 is particularly handy because also introduces the fact that it's a color quantum number, which says the asymmetric part of the wave function of this kind of things. But if we are using SU3, that means it's a non-abelian theory. That means that gluons can also couple with each other. So they're not just like photons. It's very important. The most important bits of QCD are the confinement of quarks and gluons and the asymptotic freedom, celebrating 50 years since the discovery of asymptotic freedom now. And then if all these bits that I just summarized are true, that means there are some strong evidences, which are, for example, the running of alpha S, or the formulation of perturbative QCD, the presence of jets starting from a gluon, or the fact that the gluons can interact with each other. So that means you can actually have 4 or 5 jets in the final state, which has been proven by colliders during the years. Actually confirm that, and also have a confirmation the fact that the color types are actually 3 by the observations and the calculation from the from the cross section. So based on this, Gross, Polzer, and Wilczek were awarded the Nobel Prize in 2004 for the discovery of asymptotic freedom. So I hope that I convinced that the QCD is cool and it's very solid. Any questions?
How do you tell the difference between a jet from a gluon and a jet from a quark? Is that something you can, well, it's something you can do probably, but just what's the mechanism for that?
You can actually, there's a very nice measurement they did at HERA. You can actually define a variable that basically takes into account how spread the results from an initial part of either a quark or a gluon can be in a detector. So the long story short, gluon jets are messier than quarks, because then if you have a gluon, it splits in a quark antiquark pair or a pair of gluons. So that distribution is broader than when you have a starting jet from a quark. So you can actually tell by this kind of measurements. I'm going to discuss it actually next week. It's a very good question. Thanks. Gary, you wanna ask it?
Yeah, so I was just wondering about you mentioned on slide 37 that the Lambda QCD parameter is found experimentally to be about 250 MeV. Do you know how they arrived at that? Was it measurements of alpha S and then plugging it into this formula that they were then able to deduce a value of lambda?
I believe so. I don't remember exactly how, but I believe so. They did. No, sorry, from the assumption from QED that's doing the data for QCD. So measurements like that one that I showed at the end, and then it actually saw that the threshold was about that value. Like I can look that up because I don't remember. Sorry about that.
Okay.
Any questions online? Last chance,
Not from me, thanks.
please. Oh, you see, you said
I think
no
you said
questions.
no for me.
Sorry, I
Okay.
said not from me. Sorry.
Sorry. What was that question?
Sorry.
Okay, so that's the end of the first part of QCD. Next week we're gonna have a look. So the way I structure the second part is a sort of recap of what we discussed today, and then we can have a look at some experiments. Like what once you have the evidence of jets, how can you use them to prove QCD, and then the same thing but for Barton distribution functions. It's going to have a sort of showcase of measurements with hopefully the right reference. So if you're curious, you can look that up online. Yeah, enjoy the rest of your day. Thanks.
Thank you.
Thanks.